So today we're going to do some various things dealing with the number of distinct eigenvalues of the graph. And so let's recall a couple of things. So we're going to talk about our adjacency matrix for today. Of course, that's where we're at, and it's a good place to be. So we have our adjacency matrix A, and the adjacency matrix, as a reminder, it's great for counting things. And so I like the fact that if you take a to the k, and you look at the entry uv, then that's the number of walks of length k between vertex u and vertex v. All right, great. So in other words, as we've said before, the adjacency matrix is the walk counting matrix. And well, if we're given a graph, let's suppose we draw a graph really quickly here, and so here's some graph. All right, here we go. Here's a graph, and there's one particular walk that people are sometimes interested in, and it's related to something called the diameter of G. And what is that? Well, the diameter of G relates to just how far apart vertices can be. And so instead of trying to give a really formal definition in terms of walks, well, we could say it's the maximum over all pairs UV of vertices of the minimum walk length from U to V. So that might not be the most intuitive way to say it, but what are we trying to do? Essentially, the goal is to say, I'm looking for two vertices that are just as far apart as they possibly can be. And how do we know how far apart they are? Well, we say, what's the walk length? How many steps do we have to take? Now, for a graph such as this, it's pretty easy to identify which vertices are very far apart. We can even spot them, and there's no claim that this is unique, but I would claim, and it's not so hard to argue, that these vertices are as far apart as possible. And I'll highlight one such walk. So, whoops, there we go. There's one such walk that connects the two. And so notice that because we're looking for the shortest walk, we don't sort of go and jump back and forth on edges or loop around cycles. We try to go there as quick as possible. So in this case, what do we have? Well, the diameter is 1, 2, 3, 4, 5. All right, so this graph has diameter 5. All right, great. Now, what can we say? Well, what does that tell us? It says, let's look at our adjacency matrix. If I call this vertex U, and I call this vertex V, well, what's true about A, UV? Well, the answer is, it's 0. Well, they're not connected. Okay, no surprise. A squared UV. Well, 0. A cubed UV. 0. A to the 4th UV. 0. And like, okay, I see a definite pattern emerging here. And what happens? Well, what about A to the 5th UV? And the answer is, it's not 0, it's positive. Why? Because there's at least one walk that takes 5 steps and gets us in between. But no walk can do it in 4. Because if there was a walk that could do it in 4, then our diameter would be 4. And so we say, okay. Now, notice I don't say 1. I say greater than 0. It's possible, in fact, it happens here, that there's a different walk that involves 5 steps that gets us from U to V. We just say there's at least 1. So the great aha is we say, well, we know what that does that tell us is that A to the diameter of G at uv is greater than 0, where uv is the pair of vertices at maximal distance, but a to the k uv is equal to 0 for k less than the diameter. All right, so, and here I'm assuming u and v are maximally far apart. So in essence, it's like there's an on-off switch. Now, we like on-off switches in math. That's really convenient for us. So we say, all right, now that we know that there's this on-off switch, that there's some entry which is 0 for a while, we look at powers, and then suddenly it's non-zero, we want to say, well, let's take advantage of that. So now we're going to detour for a second and talk about our characteristic polynomials. So what is that? Well, oftentimes this is used when we're trying to compute the eigenvalues of a matrix, so in particular, say the eigenvalues of the adjacency, or whichever graph matrix we're interested in. And so that's found by taking the determinant of, well, I'll call it xi minus a. And this is a polynomial. You expand it out, it's a polynomial in x. You set it equal to 0, solve for your eigenvalues, life is good. Now, one nice thing about our characteristic polynomial, we'll call this p of x, is that there's this beautiful fact that says, well, what happens in a polynomial? You take x to powers, in other words, you're multiplying powers of x, and you add them together. Well, so really, what can you plug into a polynomial? You can plug in anything as long as you're allowed to multiply powers together, and you're allowed to add. And so there's this nice fact which says, hey, you can plug in a matrix into a polynomial, and when you plug in a matrix, what comes out is the zero matrix. So when you plug in the characteristic polynomial into, when you plug the adjacency matrix into this characteristic polynomial, you get 0. Now, of course, the non-proof, because the non-proof is really easy to give, is you say, oh, yeah, that's determinant of a minus a, and determinant of a minus a is the determinant of the zero matrix, which is 0, right? Right? No, the proof is not that easy, because what happens is, remember, here, this is 0 as a matrix, and when we talk about saying things equal to 0 here, we're talking about 0 as a number. And so that's a slightly different thing. So be careful. The proof is not hard, but it's not trivial either. Well, now what we'll do is say, okay, so we know that there's some polynomial that when you plug a in to that polynomial, you get 0, namely the characteristic polynomial. There's this related fact, which is called the minimal polynomial. So the minimal polynomial, this is, I'll call it q of x. It's the polynomial of smallest degree, and we want a non-trivial polynomial here, but polynomial of smallest degree, so that q of our matrix is equal to, again, the zero matrix. So when we talk about minimal polynomial, we're talking about minimal polynomial of a matrix. And we say, all right, can this be computed? Well, it turns out the answer is yes. So when we're talking about a nice matrix, keeping it symmetric, keeping it real, in other words, the kind of matrices that we've been talking about, it reduces to something very pretty. And so we have the following fact. Namely, let lambda 1 up to lambda k be the distinct eigenvalues. And so at this point, we say, look, don't worry about multiplicities. I just want to have just the numbers. And so, for instance, if we were doing the complete graph, Well, that has n eigenvalues, but only 2 that are distinct, namely n minus 1 and minus 1. Then we can say that q of x means what? Well, it's going to look like x minus lambda 1 product up to x minus lambda k. So, in other words, if you were to think about what's happening with this original characteristic polynomial, it actually factors, right? The roots are what gives us our eigenvalues, but it looks like the following. It looks like x minus lambda 1 to the m sub 1, x minus lambda 2 to the m sub 2, all the way down to x minus lambda k to the m sub k, where the lambda i's are the distinct eigenvalues and the m's are their multiplicities. So the difference between the characteristic versus the minimal when we're dealing with something that's real symmetric is you just drop the multiplicities. All right, good. So now we have our notion here of a minimal polynomial. Okay, well, how can we use that? Well, if we were to expand this out, what would it be? Well, this would be a polynomial of degree k. And so what we have is that q of x looks like x to the k minus, we'll say a k minus 1, x to the k minus 1, and all the way down to minus a1x minus a0. Now, remember, what does our polynomial do? Well, the minimal polynomial by definition says that q of a, well, you can plug in and you'll get the zero matrix. So we plug it in. A sub k minus 1, a to the k minus 1. So little a's are coefficients, and big A's are, of course, the matrix. And this A0 isn't a number, it's the identity, and we get the zero matrix. All right. Or, and this is the key for what we're going to do in just a second here, we rearrange it. And now we'll see the reason why we had all these minuses. It says that a to the k is really a linear combination of all the lower powers. And so we say, okay, well, that's kind of cool. That's kind of cool. But in fact, you can go one step further. You say, well, look, it's not only true that a to the k is a linear combination. You can, in general, do the following, which is to say, if L is greater than or equal to k, then a to the L is some combination of a to the k minus 1 all the way down to the identity. Now, the argument for this is basically induction. You say, all right, what happens? Well, we know it's true for a to the k. That's the minimal polynomial. Now, imagine multiplying both sides by a. Well, if you do, you'll get an a to the k here. And then we can replace that a to the k by what we have here. And then everything is now in degree k minus 1 or less. And then repeat. So we can always reduce down to these terms. In other words, all the powers of a to the L are nice linear combinations of our pieces here. All right, that's good to know. That's good to know. Now, relating this back to what we were talking about. So remember, if we come back here, we have this on-off switch where a to the diameter of g, it has to be positive, but a to anything less than the diameter is 0. All right. So, what's our great aha? Well, we do the following. We're now going to look at a to the diameter of G. And we'll look at the UV entry, and then we'll do the same thing on the other side. And look at the UV entry. All right, now we know for sure that on this left-hand side that this is positive, because here the UV are not just any pairs of vertices, but pairs of vertices maximally far apart. So what does that say? That says that, lo and behold, we need some UV entry of a to the k minus 1 down to identity to be non-zero. Because if all of them are 0, well, we have something non-zero equals something 0, hopeless, hopeless. And now we just tie these two ideas together and we say, okay, well, what's true? Well, what's true is that we need to have that k minus 1 has to be greater than or equal to the diameter of our graph G. All right, well, why? Well, suppose not. If not, in other words, k minus 1 were less than the diameter of G, then what would happen is that all of these terms would all be 0, because you hadn't built up enough to have the terms actually work. And so we have our great aha moment, which is to say we have this lovely fact that if you look here, so what is k, by the way? K is the number of distinct eigenvalues of your graph has to be strictly greater than the diameter of your graph. And there's our result. There's our result. All right, so this is a nice relationship. So we say, okay, so if our diameter is large, we have to have many distinct eigenvalues. And if our number of distinct eigenvalues is small, well, then our diameter has to be small. Okay, so let's just sort of test this to see what's happening. So let's pick a graph, and of course we'll pick a graph that we've seen and we know the eigenvalues for. And all right, we'll do Kn. And what do we have? Well, what are the number of distinct eigenvalues? And what's the diameter? Well, and for Kn, the number of distinct eigenvalues is 2. What's the diameter? 1. All right, well, that's not so bad. How about for complete bipartite graphs, Kmn? In that case, we've worked it out. The number of distinct eigenvalues is 3. The diameter is 2. How about a cycle? All right, well, this one you have to think a little bit about, but what you can show is that it's the ceiling of n over 2. All right, great. Well, how about the number of distinct eigenvalues? Well, it's about, number of distinct eigenvalues, it's the ceiling of n over 2. The diameter is about n over 2. There's a little bit of, even versus odd. I'll wave my hands here. See, here's me waving my hands. And it works out like you need it to work out. All right, well, what about the path? Okay, how many distinct eigenvalues do you have? Well, it turns out you have n. What's the diameter of that? It's n minus 1. And now you can actually prove that the number of distinct eigenvalues of the path is n without even knowing what those eigenvalues are. If you think about it, say, okay, let's suppose we look at the path, and you take a look at the matrix lambda I minus a. Well, what does that look like? It looks like you have lambdas down the diagonals and minus ones above and below the diagonals, and otherwise you have 0. And now, what can we do? Well, what we can do is look at a little submatrix, namely remove the first row and the last column. And if you look at that submatrix, what it looks like is minus 1 down the diagonal, 0's below, and then lambda's just above the diagonal. And this has full rank. So in particular, lambda I minus a always has rank n minus 1. And so the dimension of any null space is at most 1. So all the eigenvalues have to be distinct. All right, cool, cool. Now, you might be thinking, wow, this is really consistent. Is it always the case that if you look at the diameter number of distinct eigenvalues, you basically are off by 1? And the answer is no. And so we'll make a little side note here for a random graph, and we're going to put random in quotes because we haven't really talked about, wait, what does it mean to be random? Oh, that's a long discussion, and one that's very subtle. And so we're going to have to hold off on that. But if you look at a random graph, the diameter of most random graphs, in other words, how many steps does it take to get from point A to point B, is, well, it's about 2. So in other words, it's very short, but the number of eigenvalues is very high. And roughly, you have a full set of eigenvalues. And so you'll see that it'll happen that you actually get a pretty big spread. So, and most graphs are random. And again, what does that mean? Well, okay, well, that's a discussion for another day. But all right, there we go. All right, so cool. We have a nice relationship here. I want to mention another result, though, that deals with distinct eigenvalues. All right, so that was our first result. Let's do a second result. And this one has to do with graphs where our eigenvalues are all distinct. So suppose G is a graph with all distinct eigenvalues. So in other words, n vertices, n different eigenvalues. All right, can we say anything about the structure of such a graph? And well, our goal is going to be to say yes, and we will work our way towards that destination. It will take us a couple of minutes to get there, but that's all right. We have time. We're not in a rush. All right, so this is our setting. Now, come back to that. Let's talk about automorphisms. Now, what is an automorphism? We want to say, somehow auto is self and morphism is form. It's a way to look at the graph and say, oh, this graph has symmetry. And in particular, what we can think of an automorphism is that it's a relabeling of your graph which does not affect adjacencies. So let's just give an example here, because examples really help us to illustrate what's going on. So suppose we have a graph here, and we'll have it with a labeling here. So I have vertex 1, here's a 2, here's a 3, here's a 4, and let's put a 5 here. All right, so here we go. Now, I claim that if we swap vertex 1 and 2, then you wouldn't be able to tell the difference between these graphs. And so I'll draw it underneath here. So first off, I'm going to draw without any labelings. And then what I'm going to do is I'm going to relabel. So my relabeling is I'm going to keep 3, 4, and 5 as they are, but for 2 and 1, I'm going to have them swap their place. Now, are these the same graph? And the answer is yes, they're the same. Okay, good. And this is an automorphism. So again, it's a relabeling, but no adjacencies are affected. And in particular, if you were to say, look, what's the adjacency matrix of this graph versus the adjacency matrix of that graph? And you would say, it's the same adjacency matrix. That's what it means to say the adjacencies have not been affected. All right, well, thinking about what's going on with our matrices, what can we do? Well, we can look at what does it mean to relabel. So in particular, I'm relabeling the vertices. I maybe should have emphasized that, but I'm saying it now, relabeling the vertices. Well, if you think about the adjacency matrix, the vertices are corresponding to rows and columns. So a relabeling, that corresponds to a permutation matrix that we can apply. So we've mentioned before how the graph is resilient to relabeling, right? In other words, if you relabel your graph, your eigenvalues are unchanged. And so what we have is a relabeling here corresponds to some permutation matrix P, PA, P inverse equals A. So think of P as your relabeling action, and then A is our adjacency matrix, so the relabeling does not affect the adjacency. All right, good. Well, what does that help us say? So we have that P times A is equal to A times P, because we can multiply both sides by the matrix P. All right, so we're in a setting here where by relabeling really says there's a nice permutation matrix. One side we permute the rows, one side we permute the columns, and the results are the same. Now, these are not our adjacency matrices. Once you permute just the rows, then that's probably not an adjacency matrix. It's when you permute both the rows and columns that you stay in adjacency matrix. So what does that do for us? Well, now let's look at the following. Suppose that A times X is equal to lambda times X. Okay. So which is to say X is non-zero, so we have an eigenvector. All right. Now let's look at A times Px. So we have this relabeling. Let's suppose that we have that relabeling coming into play, and we apply it. Well, what can we say? That's the same as A times Px, but we know A times P is P times A. So that's PAX. So that's P times AX, and this is us going in slow motion. Normally we don't do it in quite this many steps. We say, look, that's P times lambda X, which is lambda times Px. Say, all right, well, great. So what does that tell us? Well, what it tells us is that if we have an eigenvector, and remember, that's what x is our eigenvector, then we have more eigenvectors. So in particular, if x is an eigenvector, then so also is p times x. And so this is not terribly surprising. It basically says, look, if you think about what a vector is in terms of a matrix, a vector is assignments of values to the vertices. And it just says, carry that assignment with you as you permute, and you're still an eigenvector. All right, well, that's great. And so one of the things it tells you is if you have lots of symmetry, then you can possibly create lots of new eigenvectors. Now, be careful here. Is x a new eigenvector? The answer is maybe, maybe, but it depends on what x looks like. And that is to say, if your x might not change under the relabeling, because it might be the case that, well, maybe x has the same values for these two vertices to begin with, and so when you relabel, nothing happened. All right, so now this is just general fact, okay? We haven't made any assumptions here about all distinct eigenvalues. Not yet, but let's do that. All right, so let's go back to here. So let's now say if all eigenvalues are distinct, and what must be true? Well, in that case, what's true is if x is an eigenvector and px is an eigenvector, what's the relationship between x and px? Okay. What is the relationship? Well, the thing is, they can't be linearly independent. So x and px cannot be linearly independent. Why? Well, if they were, then you would have at least dimension 2 in your eigenspace, right? Because you have two different vectors. And that's not possible, because to say all eigenvalues are distinct says, look, each eigenspace has dimension 1. So that says that if I look at p times x, it's some multiple, we'll call it mu times x. Now, what can mu be? Well, it's not too hard to figure out. P is a permutation matrix, and there's a lovely fact that says if you keep doing the same permutation over and over again, eventually you have to get back to where you started. And so this is like card tricks use this, for example. And so what we know is that p to the kx has to equal x. So for some, if you take the order of the permutation as k, where here that's, it's something, right? Then you have to get back to where you started. Well, that has to equal mu to the kx. Well, okay, so now we know that this mu has to be a root of unity. All right, well, what does that tell us? Well, it has to be a root of unity, but px is real, x is real, so the conclusion is mu is plus or minus 1. So in other words, if we know all our eigenvalues are distinct, then applying any automorphism to the eigenvector just either gives us the same eigenvector or the negation. Well, so what does that tell us? It tells us that p squared of x is always equal to x. And this is for any automorphism p. Now, I will say that at this stage, we really haven't used the fact that all eigenvalues are distinct. This is just true if you have an eigenvalue which is distinct, and you look at it, you come to the same conclusion that, look, that has to be true. As if you have an eigenvalue which is distinct, then it has to be the case that either the automorphism gives you back the eigenvector or it gives you the negation. But what does this say? Well, that's for any automorphism group for that eigenvector. Well, now we say, hey, well, this is true for all eigenvectors. And so, okay, so what's that tell us? Well, it tells us that the following, namely, but the eigenvectors are a basis for all of our space, because we have a nice full set of our eigenvectors. And so, what's the punchline? Well, what we know is that says that, look, p squared times anything gives you back the same thing, so p squared is equal to the identity. So our great aha, and this is the punchline, we start up here, we'll end it down here, so our great aha is to say that all automorphisms they have order 2. Unless, of course, you're to the identity, in which case you have order 1. So if all our eigenvalues are distinct, then any automorphism has to have order 2. And okay, well, cool. Let's just look really quickly at one case that we already know for sure, is we know the path. And so we'll just draw a path. Let's just make it 5 vertices. So here's our vertices, 1, 2, 3, 4. Whoops, 1, 2, 3, 4, 5. I know how to write 1 through 5. All right. Does this have any automorphisms? And the answer is yes, it has exactly one, and which is you put it backwards. 5, 4, 3, 2, 1. So here, this is an automorphism. And notice that for this automorphism, it has order 2, which is to say, okay, if you do the same step that got you from there to there, do it a second time, you'd get back to where you started. So to say automorphism has order 2, in 2 steps, if you did the same action, you'd get back to where you started. Now there's a nice corollary, and what's the corollary? Well, you might say, wait a second, is that even how you spell or say corollary? And I was told when I was a student that the proper English pronunciation is you count back from the end 3 syllables, and that's where you should be putting your emphasis. So corollary, but anyways, that's a different story. So the corollary says, if a graph has an automorphism, which automorphisms have orders, so the order is how many times it takes to get back to where you started, of order at least 3, then it must have a repeat eigenvalue. In other words, you cannot have all distinct eigenvalues if you have some nice symmetry. So only when you have graphs where there's not a lot of nice symmetry will you have graphs where you have eigenvalues distinct. You're allowed a little bit of symmetry, but not much. And so, as one quick example, if we look at, say, this graph right here, this is a triangle where you add a leaf onto each one, then our conclusion is, without any work at all, this must have a repeated eigenvalue. Now, I don't know what it is, and I'm not making a claim that there's lots of them. I'm just saying there must be at least one of them. Because why? Well, notice, the automorphism is rotate 120 degrees. Now, of course, that's, if you just think about graphs as sets, rotate 120 makes no sense. But in this case, if you think of graph as picture, then rotate 120. Yeah, okay, I believe it. Makes sense to me. And so there you go. And so yeah, that's a nice fact. You can learn a little bit, in fact, more than just a little bit, about the graph structure by saying, oh, do I have repeated eigenvalues or not? And oftentimes, when you have symmetry, it's a great way to find eigenvectors, right? Because once you find one eigenvector, you can apply your symmetries, your automorphisms, and see, wait, do I get more? And a very simple case of that, we've kind of already done it, and I'll just point it out since we have a few minutes here, is you might remember that we talked about complete bipartite graphs. And so you have your two sides, and you put all possible edges in between. And normally we don't even do that. Normally we just do a squiggle. There we go. And you say, okay, well look, here's a 1 and a -1. And everything else is 0. All right? So these are our eigenvectors, or n eigenvector. Now here's my claim. I can do automorphisms and get more eigenvectors, right? Well, how? Well, come to this side and say, look, I can relabel these vertices arbitrarily because they're indistinguishable. That's in some sense what an automorphism is. It's saying, hey, these vertices are essentially the same. And so what does that tell us? Well, what I can do is applying an automorphism where I'm doing a relabeling over here is I let any vertex be a +1, any other vertex be a -1, and I have an eigenvector. And so in this way I can make more eigenvectors. And so that's just something to perhaps be on the lookout for. And all right, well, that'll be it for today, and we'll pick up again next time. Hope you have a good day.